performance in a specific environment. But of course, this is very complicated because there's a lot of storage involved if you want to capture light field of a scene, so this is often not practical. One thing which has been shown by Shai and Sherman in the SIGGRAPH 2000 paper, that we can approximate the frequency spectrum of a light field by interpreting it as a collection of frontal parallel planes, and then we can interpret the frequency spectrum in terms of a reference view. And if we know something about the scene, for example, the depth of motion distributions, then we can use this to approximate the power spectrum in the light field and use that in our formalism. Because of time reasons, I don't want to go into detail about this. It's all in the paper. I mean, sometimes we are not interested in a specific environment, but we would like to know something about maybe an average environment. And there has been a lot of work done lately on natural image statistics, and using the approximation from the bullet before, we can also extend image statistics to light field statistics and plug them into our formalism. So at the end, I would like to compare the prediction that our algorithm does to some true cameras. Unfortunately, we are still in the process of building these kind of cameras, so therefore I won't be able to show you any results that compare our prediction to some real implementations. But there's a way how we can simulate cameras or arbitrary camera geometries, and that is if we take a highly sampled subset of the space of light rays, in this case an epipolar plane volume, I can simulate a plane of motion or of a line camera inside of this by resampling appropriately. So, for example, this is now again the axis of view positions. These are the axis of view directions. So if I look at one line image at a time, and now I move its position through the light rays, this corresponds or can correspond to a rigid motion if it's chosen correctly. So now if I move multiple cameras at this, or multiple slices at the same time, I can simulate a multi-camera setup. And by varying the camera spacing, here as denoted as delta x, for example, the number of viewpoints, the field of view, which would be kind of the size of the segment that it sees at a time, and also point spread functions, we can simulate how a camera would behave. And for planar motion estimation, as we saw before, we kind of defined a hierarchy on where we have on one axis the spacing of the viewpoints, and on the other hand we have the field of view. So in here for planar motion we estimate the relative error and the rotation angle, and on the left we have the simulation result by resampling epipolar plane. And as expected, if we have a small field of view, the aliasing errors introduced by increasing this camera spacing have a fatal effect on the accuracy. But as soon as the field of view increases, the estimation becomes much more accurate and stable, and the effect of the errors is not as strong. In our simulation, we're not able to capture, to have an exactly accurate reconstruction, but the qualitative nature is captured. We're working on refining this prediction by making better, modeling the camera parameters better. But we can also, instead of field of view, we can now vary arbitrary parameters. For in this case, we change the blurring factor in the perspective images, where, like, for example, if you have a larger lens or you have more depth of field, something like that. And what we see is that the more we increase the blur of the optics, which under normal circumstances would reduce in a degraded image, which might not be as useful for computer vision application. But now for motion estimation, it actually increases our performance because we take care of the aliasing errors. So that's what I pointed out earlier, that the best image in conventional terms might not be the best image for a given task, but that we should measure the task performance of a camera in terms of what we truly would like to accomplish. And here we see again our prediction by our error estimate. Especially in the areas of high noise or high camera spacing, it is not very accurate, but that also that our sensitivity analysis only uses a first order analysis of like an error and variables model, so therefore the nonlinear factors from large errors are not affected. So for current and future work, as I said, we're currently building different instances of polyoptic cameras, and I'm looking forward to we finally able to compare the prediction or the framework we have here with the real-world implementation. We also work on extending the camera metrics that are described here for the case of 3D motion estimation to other kind of vision problems that are expressed or encoded in a direct manner in the visual structure of the space of light rays, like 3D photography, object segmentation, independent motion detection, etc. And finally, we would also like to expand the notion of the sampling analysis from a regular alignment of cameras, as we need so far to apply conventional image, to be able to extend the image processing analogy to non-uniform sampling so that we can take into account the distortions in cameras, for example, at omnidirectional cameras. So, as a summary of everything is collected here, we think about the visual task we are trying to solve, look at it, how it is encoded in the space of light rays, which leads to a qualitative classification of cameras. To quantify this hierarchy of cameras, we then analyze the sampling structure of the different cameras, which then leads to a quantitative coordinate system on the space of cameras, which is task, scene, and camera specific. Thank you very much.
Okay, there is time for one short question. No questions? Okay.
Should I wait for the microphone?
Yes, please.
It's very nice work. One thing you had in your conclusions you mentioned is that if you increase the camera spacing, the aliasing gets worse. Is this because you're using sort of a differential infinitesimal motion model? Because my intuition generally is if you're trying to estimate motion or something, the wider the baseline, given that you can match, the better you do, as long as you're doing some sort of discrete matching.
Well, the model that I used here was basically if you have multiple viewpoints, you try to solve the motion problem as an image registration problem. So therefore, if you want to basically find out if cameras, or if the different light fields that you captured are similar, if they are sampled very coarsely and you lie right in between, there's not that much information how you can compare it. But of course, if you now combine it with, for example, depth estimation, then as was shown before, if you know something about the depth, like in your work, you can interpolate light fields very well because the structure is very constrained. So that is something, depending on the complexity of the algorithm that you would like to apply, you can definitely, this is now, if I want to have kind of a one-shot algorithm purely based on image measurements, I want to estimate my motion, then I can define such a hierarchy or such a measure on the space of cameras. The more complex the tasks are, or the more, it is basically kind of, instead of focusing all the work on the algorithmic side, see what we can do on the sensor side. But of course, there's still a large variety of how we can shift our emphasis and to improve it. And of course, it's best if we combine both, choose the best for both worlds. Thank you.